So this is SAC 1 2012 and it's the calculator active analysis question. So we have a function here and there's a graph drawn of it, and the first question says state the coordinates of the x-intercepts of that. And so what I've done is entered that function into the calculator and defined it as f of x. And since the x-intercepts occur when f of x equals 0, I'm just going to solve for that in terms of x, and I get x equals 2, x equals 4, remembering that the coordinates are not x equals 2, x equals 4. The coordinates are 2, 0 and 4, 0. The second two parts, parts B and C, talk about how many x-intercepts this particular function g of x can have and how many stationary points. And the only difference between g and f is that this parameter here in the middle is an a. It's not really that useful to have a calculator with this part, but a couple of graphs that I've drawn might help explain what I'm talking about. So how many x-intercepts can this sort of function have? This first red one is where that parameter is 4, and the blue one here is another graph of the same function except that that parameter is 12. So you can see how changing a, increasing a, drops this stationary point of inflection and it becomes a local minimum. So we can have two x-intercepts. If that local minimum just touched the x-axis, you'd have 3 x-intercepts, and finally, like this blue one, you'd have 4. So the possibilities are 2, 3 and 4. With stationary points, you can have 3 stationary points, as this blue graph shows. You can have 2 stationary points, as the red one shows. But sometimes this stationary point of inflection is in fact a point of inflection, but it's not a stationary one. So that if you take the derivative of this, for example, you don't get 0, or you can't solve. And they are possible. So it is possible to get just one stationary point here, 1, 2 or 3. Part D, find 4 values of a such that the graph of g of x has exactly 3 intercepts, and that's g of x here. And that's quite difficult. It's exactly 3 x-intercepts. We've already got 2 here, and so we'll either get 1 out of this expression here, or we'll get a repeated expression. In other words, we could get a factor x minus 4 in here, which would have 1, 2, and then a third out of that as well, or a repeated factor where x minus 2 is in fact repeated. So one suggestion for that is to explore what happens if we introduce this variable a. Let's define just this section here as g of x. I've only got that quadratic there because that's really the one that we're interested in. We've already got these other 2 factors. And let's see what happens when we get another factor that is exactly the same as these other 2. The first one would be perhaps when we get x minus 4 as a factor. So g of 4 would be equal to 0. So I want to solve this, but I don't want to solve it in terms of x. I want to solve it in terms of a. So I get a is minus 14. So one of the values of a, where this graph has exactly 3 x-intercepts, would be a equals negative 14. The other repeated factor would be when we get x minus 2. So I can just enter there and we get minus 10. So that's 2 of the 4 values. The other values are going to be when I solve not for any repeated factor, but when I find out what the answer is to this particular expression, but with respect to x. And there I get these values in terms of a. But if I really only want one of these to be a solution, And to get one solution, I basically make the discriminant equal to 0. And when I do that, I now solve for a again, and I get minus 4 root 6 or 4 root 6. So my four values of a, where I get three intercepts, are 4 root 6, minus 4 root 6, minus 14 and minus 10. So that's part D. For part E, we make a equal 5, and there'll only be one stationary point. We might want to state the nature and the coordinates of that stationary point. So we might go back to the graph. These x-intercepts are in fact set. It's only this parameter that's changing and is now a 5. So it may be that this particular inflection drops, as we saw with this shape graph here. So let's make a equals 5 to begin with, and perhaps what we can do is just copy this, paste it in over here, and change it to a 5. We can define that as anything we like. We can now go ahead and define it as g if we like, and that will override what we've done before. I'm just going to change that to a g, not a zg. So we just check, that's fine. And we basically want to find, if we look at this graph, we want to find the minimum value that that's going to be. To find the coordinates of that stationary point. We can do that by using fmin. So there's fmin, and the expression I want is g of x, and I'll go OK. And basically my minimum value for g of x with respect to x across the whole domain is minus 52.5, that's my y value, and my x value is 3.2. So the coordinates are 3.2 minus 52.539, because it's 3 decimal places. So minus 52.539 is the y value, x value is 3.211. The nature of the stationary point is it's a local minimum. We now want to find out the value of a such that this function here passes through the point 615. So I'm going to once again use this part of the function, or I can just type in g of x. I want to use that again, but this time I don't want a 5, just want an a, the variable a. And it doesn't matter that I've defined something else as g, because I'm not going to use it again. I may as well just define this as g, as it says in the example. And I want to find out what the value of a is when x is 6 and y is 15. So it's really like saying g of 6 equals 15, but what's x? Or what's a when that happens? And so I want to solve that with respect to a, and I get minus 913 over 48, which is the answer to F.